So now, how can we measure all these different types of aberrations? There are a couple of different types of wavefront sensing technologies. For the interest of time, I'd like to focus on Sharp-Hartmann type wavefront sensor, which has been the most popular aberrometer in the field of ophthalmology and optometry. Here's a diagram showing how this wavefront sensing technique works. So first, you put the very low power of the laser beam onto the retina, and then light gets reflected from the retinal surface, passing through the eye. And if the eye is optically perfect, in other words, no aberrations, you would expect to see perfectly plain wavefront. So this wavefront goes into the array of small lenslets and divide that each lenslet creates a small spot on the detector plane. So in two-dimensional space, you will get this kind of a regularly spaced spot array pattern if the perfect eye is being measured. So now, if you measure real eye, which is aberrated, now same principle, you send the laser beam into the eye, wavefront coming back out of the eye, and now you have a distorted wavefront entering the same lens array. Because of the distorted wavefront, now individual spots are no longer formed on the center of each lenslet. It creates this kind of irregularly spaced spot array pattern. So now by comparing these two images side by side and analyze them, you could actually measure how much individual spots are displaced from your reference point, which is from the perfect eye. So the size of the magnitude, size of this displacement in X and Y direction corresponds to the average wavefront slope entering the individual lens. So basically that's how we measure aberrations from the individual displacement of the spots. So this is how the Sharp-Hartmann wavefront sensor works. But when we develop this type of wavefront sensor, so we have to consider a couple of important factors to develop optimal measurement performance of the wavefront sensor. Measurement sensitivity is one of those important factors. So what it is how small magnitude of aberration this wavefront sensor can measure. So that's basically wavefront measurement sensitivity. And the other important factor is the dynamic range. This is very much an opposite concept. How large, what's the maximum magnitude of aberration this sensor could reliably measure? So these are the two very important factors. Quite often, they have a very interesting trade-off. So when we do that, if you have a long enough focal length so that the small deviation of the wavefront slope could cause the sufficiently large enough displacement of the spot so that program could detect that displacement, so that tells us, this wavefront sensor has enough measurement sensitivity. But what if you put very large aberration into the same wavefront sensor? Now what happens is spot displacement is now too big, so the spot from this area and moving into the adjacent centroiding area, so this would cause a problem because we can't find this spot in this area. Or even worse the case, and adjacent spot actually, those two spots are cross over each other. So you could find the spot, but this spot is actually coming from this lenslet, not this lenslet. So even if you can find the spot, if you don't have this crossover information, you wouldn't be able to detect the spot locations correctly. You can kind of see that by having the very long focal length, you have enough sensitivity, but you're going to lose the dynamic range. So to overcome this dynamic range issue, one of the simplest thing you can do is to increase the lenslet size. Therefore, your centroiding area zone gets much larger compared to this smaller lenslet. But problem here is that now the lenslet size is too big. The wavefront shape over this single lenslet is averaged out. Now you don't really have reliable displacement of individual spots. You're basically losing the high spatial frequency information that was included in the original wavefront. The other option you can take is to make the focal length very short so that relative displacement of the spot is much smaller than when you have a longer focal length. In this case now, because you have such a short focal length, now you don't have a sufficient measurement sensitivity. So you may have a trouble measuring relatively small magnitude of aberrations. So in summary, if you start with too small lenslet size, which creates many, many spots, now you would have a good sampling resolution because your lenslet size is small. But on the other hand, you will have a low dynamic range because the centroiding area becomes very small. Now, to avoid or overcome this problem, you could increase the lenslet size, but now it becomes poor resolution, which will be conflicting with the good resolution you had originally with the small lenslet, or you could make the shorter focal length lenslet. Now you're losing measurement sensitivity. So it's a very kind of complicated or headache when you optimize the wavefront sensor. So now, because the first step is to determine how many aberrations do we need to be able to measure to reliably represent the eye's aberrations. So we did a study about 15 years ago where we actually fit the corneal topography with a different number of aberrations, and we look at the errors in terms of residual root mean square, and then we varied the different number of aberrations. So by having this curve, we could actually say, well, if I want to have error below 0.1 micrometer, then you draw the line and figure out how many coefficients do we need. In this case, we need the 55 aberration coefficients, but maybe the 0.1 micrometer is a too tight threshold. You could use actually 0.2 micrometer as more realistic threshold. Now, you only need 35 Zernicke coefficients to describe types of aberrations you want to measure. The other factor we need to consider, even if you can measure many, many Zernicke coefficients, the question is it really worth trying to correct all those aberrations? Answer is yes, only if you could correct the decentration rotation of your correcting up. But if there is an uncontrollable amount of decentration rotation, it may not be the best strategy to correct all these aberrations. So this diagram illustrates that. So imagine that your eye has a spherical aberrations, and your lens has opposite sign of aberration, but in this case with the vertical decentrations. If there is no decentration, this residual aberration map should be single color because it will be zero residual aberrations. But because of the decentration, that decentration actually induces astigmatism and defocus and coma. If the decentration is too large, then maybe residual aberration is actually larger than the original aberration you're trying to correct in terms of the impact of those aberrations on the image quality. The vertical coma, same story. In this case, a decentration and plus rotation, then you get induced a lot of different types of aberrations.